Hi everyone. Last time we did an analysis of a nonlinear two-dimensional system as an example. And I'll write again the system in our findings. So if you remember, it was not easy to find a fixed point for this, but we were able to draw the null lines and then find where they intersect. So we had this. We had this parabola as the x null line, and we had this curve as the y null line. And we were able to first find the directions of the arrows along the null lines, of the arrows meaning the vector field that applies in this system. Okay. So it looks something like this. And then immediately we knew this was a saddle point, because then in this region you have trajectories going this way, this region this way, here this way, and here this way. So you see that in the area surrounding the intersection, we have the pattern for a saddle point, and also we found a Jacobian, and then we found the eigenvalues, or the trace and determinant. We could classify this as a saddle point. We could find the eigenvalues and the eigenvectors. And we drew the eigenvectors. They were they looked like this. They were 1 square root of 3 and 1 minus square root of 3. And then it was just kind of filling in the arrows that represent the trajectories. I'm doing the eigenvectors in black and the trajectories in blue. And here I said that you should try to draw the arrows over the whole plane, okay? And the only thing that you need to comply with is that the directions on the null lines will be obeyed, okay? So you can draw trajectories all around here, but if your trajectory is anywhere vertical, it must be on this null line, the green one. And if anywhere it's horizontal, it must be on the red line. So there can be no change in direction other than on the null line. Okay? If a trajectory has a general direction of right, then it cannot start going left unless it's passed on the green null line. And the same for up versus down. So we said that, first of all, we know on the eigenvectors, we know what happens. Okay? Like this. And also that the eigenvectors, they don't continue on forever in the nonlinear system. Farther away from the fixed point, this, for example, this what's called the stable manifold of the saddle can curve. And we see that it must curve because if we just continue it, it will intersect with this null line, and it's not possible. Okay, on this null line there is only one direction that can be. So we might think that it's something like this, and so in this area we have directions that are diagonal, and then we could think that here we have this change in direction, or diagonal and then vertical and then changing direction to go over there. And the same with directions coming from here, with trajectories coming from here. They might look like this or like this, and basically everything kind of agrees with what happens with the saddle because it's the only fixed point here. So trajectories can come from this area, and they diverge. They avoid the saddle, and the same from the other side. So now I'm going to show you a simulation of this. Yes?
When you drew the not near the fixed point,
Yeah.
it was more or less a guess. Like you
Yeah.
could have drawn it like this.
Where?
This line that goes down.
Okay.
No, not like if you start at the fixed point,
Yeah.
you go down, not
Here?
that way, to the
That one?
to the left.
The lower
This
lower
one?
part,
Or goes
you drew
into
it
the
like,
fixed point?
like this.
Yeah.
But you could have drawn it like a parabola if you wanted.
No.
Or something.
No.
Why? How?
Because,
do you know?
okay, if it's a parabola,
No, not a parabola.
yeah, but I know what you mean. If it's doing this, then here it is horizontal. And that must happen on this place here, on this point, this line, the red line. It cannot be horizontal on the red line and then continue there. You see what I mean? If I have my my red line, you're saying that a trajectory that goes into the saddle above the red line might go like this. But this cannot happen because here there is a point where it is horizontal. And this must happen on the red line. Okay?
But it can go like with a different slope or...
Yeah, with a different slope, but to the right and upwards. Always to the right and upwards according to what happens in this region between the null lines. So I'm going to show a simulation of the system, and you can see what the trajectories look like. Is this enough? Okay. Oh, it's a little hard to see the null lines. Let's do it differently. Okay, can you see it? Yeah. So here I have this little simulation that allows me to pick initial conditions, points on the plane, and then we'll see where the system goes from them. Okay, so let's see what happens near the saddle point. You can see that the change in direction occurs on the null line. from the other side, looks like this. So we can see the pattern of the saddle emerging. Okay. And if we go to other places, you can see that my lines, this line, for example, it goes in the direction I told you, and it does its turn on the milk line. It goes over there. And this too. It does its turn here. Okay?
So that means like if we, like the line I asked you about before goes between them?
Yes. It's really hard to find this line. I mean, probably I won't be able to put my initial condition on this stable manifold. But I can put things around it, and then you can see approximately where it is. It's formed by, I mean, you can see it emerging from all these trajectories that are actually diverging away from it. So it's somewhere, it passes somewhere here.
Hadn't you started on it, you would just move directly in the direction of the fixed point?
Yes, you would go into the fixed point. And there's another line like that here.
It also does the same?
Yeah. So what I could do if I really want to find it is reverse the direction of time. I mean, put minuses instead of pluses in my equations.
Okay.
And then all these trajectories would go backwards. So I would start here, for example, and I would see it going into this line. It's a trick that maybe we'll see with the next topic we're covering. So this is what the system looks like, and what I want you to see is that what I want to say about this is that you don't have to know the exact trajectories. For us, it's okay if you draw these and maybe a little more trajectories, and it's a kind of game where you kind of play. You start from here, and then you think, where should this trajectory go? And you really don't need to be exact. Okay, we're looking for the trends in the system. But it's nice to see how in this nonlinear system there is a saddle and how things look far away from the saddle. You see that they might look different from the linear system of a saddle. Okay. The next example we're going to see of a, let's see, okay, I can turn off the projector for now. Next example we're going to see is a population model, which is a nonlinear two-dimensional system. And I think it's nice to see an example that has physical quantities behind its variables, because it gives you some, I think it gives you more motivation to study the system and to understand dynamics in general, understand the theory so you can analyze models that have meaning in the real world. Okay, so this is the Lotka-Volterra model. And it's a population model describing two populations that have an interaction with each other. So X will represent rabbits, and Y will represent sheep. And they are both living in the same environment. They both feed on the same source of nutrition. They both require grass. So they have a competition between them. Okay? So the equation for the rabbit is this one. This part is just a logistic growth, okay? It's like writing 3x times 1 minus x over 3. So then you would have a rate of growth will be 3, and the capacity is also 3, according to what we learned, okay, when we covered the logistic growth in one-dimensional systems. Now remember that in the population models that we do here, at least in this part of the course, the variables are let's see, continuous, okay? We don't care that there can be only 1 or 2 or 3 rabbits. Or actually, we assume that we measure in units that are much larger than 1. Okay, so maybe our units are thousands of rabbits or hundreds of rabbits. So we don't care about the fact that actually population is discrete. So this capacity of 3 doesn't necessarily mean 3 rabbits. Okay. Okay, and this term is a competition. It means that if the population of sheep is large, then it makes the population of rabbits decrease. Okay, it gives you a negative feedback on the x dot term, and it's not the population of sheep alone. It also depends on how many rabbits there are. Okay, so the product of sheep and rabbit is what determines how much competition is present in the environment and how much the population of rabbits will be affected with some prefactor that controls the strength of this competition, meaning how much of a competition the sheep pose for the rabbits. And the equation for the sheep, y times 2 minus x plus y. So, no, it should be minus y, of course. So you can see 2, you can take outside and adjust everything accordingly, and that will be the rate of growth. So in this model, the sheep reproduce slower than the rabbits, like everyone does. And this term it actually contains the carrying capacity. So the carrying capacity is 1/2, and that also makes sense because you can have less sheep per unit of area than rabbits, where the capacity is 3. And and this is a competition. And again, basically it has a factor that's smaller. So a rabbit would pose less of a competition for a sheep than a sheep would for a rabbit. Okay. Okay, and as always, when we deal with populations, we say they are non-negative. So we just don't go into the negative ranges. We just don't analyze this. Okay, there's no use. Okay, so it's very nice that all these things have some meaning in the model, but we can treat this just like any nonlinear system. And first, we would like to find the fixed points. Okay. So immediately you see that when x equals 0, this makes everything here 0, and when y equals 0, same. So 0, 0 is one fixed point that we might have. And then if x does not equal 0, then we should check what if this term here equals 0. So we get this condition. And 2 minus x minus y. This is for the other equation. Equals 0. Then we get x equals 2 minus y. And then we could start doing the combination. So what if x equals 0, but y does not equal 0? But still, this equation can have a 0 with this. So we could have a fixed point at 0, and then 0 equals 2 minus y, so y equals 2. So then what if y equals 0, but x does not equal 0? So still we might have a 0 if this term is, if this condition is met. I have here, what? Yeah, okay, I got confused. And then what if neither x or y are 0? So then we would combine these two conditions, and we would get 1, 1. If y is 0, no, this does not have to be 0. This term does not have to be 0 because this is 0. Okay. Okay, so let's plot this. I have a fixed point that's 0, 0, 3, 0, 0, 2, and 1, 1. And I don't know the stabilities yet, so I leave them empty. Now we would like to find the stabilities and later the eigenvalues. So we can write the Jacobian of the system. Let's write the equations without the parentheses. And so the term here is 3 minus 2x minus 2y. Then the next term is the derivative with respect to y. Then we have the derivative of y dot with respect to x, and the derivative of y dot with respect to y. That's 2 minus 2y. There. And then once we have the general form of the Jacobian, we would like to evaluate it at every fixed point. So j at 0, 0 is okay. And this is really straightforward. I mean, this has as eigenvectors the normal vectors, and as eigenvalues it has 3 and 2. And you see this is an unstable fixed point, an unstable node. Okay.
How do you see that?
Because there are 2 positive eigenvalues, so everything goes away from this point. And I can draw the eigenvectors. Let's just divide them by 1/2. And I have growth along these 2 eigenvectors. Okay. If I would like to let's do this in red, to draw trajectories going out of this point. I have trajectories going on the axes, and in between we need to consider which one, for example, which one is the larger eigenvalue. That's lambda 1. So this means that far away trajectories will be more parallel to the first eigenvector. Okay? Now, I will evaluate J as the next fixed point. Okay, 0, 2, this is minus 1, 0, minus 2, 2, minus 4, minus 2. Okay, so here I don't know immediately the eigenvalues and the eigenvectors. So I can find that the trace is minus 3 and the determinant is 2. Okay. Minus 3 and 2. Somewhere here. So this is a stable node. Okay, maybe it's a spiral. I can do a calculation to find that. But I'll just go on and find the eigenvalues. So I have lambda, remember it's a trace plus minus square root of trace square minus 4 delta divided by 2 minus 3 plus minus square root of 9 minus 8 over 2. So I get lambda 1 equals minus 1, lambda 2 equals minus 2. It's not a spiral, right, because these are real eigenvalues. If we add complex eigenvalues, then it would be a spiral. So this is a stable node. I can fill it in. This is 0, 2. Okay. And then I would like to find the eigenvectors. So writing this minus 1, 0, minus 2, minus 2. This is for V1. R1, S1. Okay, so I get minus R1 equals minus R1. Minus 2R1 equals 2S1. Yeah. Okay. Yeah. Minus
No, on the right side of the equation, the second equation.
this one?
No, the second equation.
Here.
Second.
Sorry.
One. Minus 1, not minus.
Yes. Right. Okay. So I got that minus 2R1 equals S1. And I can write that V1 equals 1 and minus 2. Right. Okay, here I used the second equation eventually because the first one gave me nothing. And for V2, then I'll use the second equation again. And it would give me minus 2R2 minus 2S2 equals minus 2S2. And then R2 equals 0. and then S can be whatever I want. So V2 equals 0, 1. So this is V2 for this fixed point, and V1 is 1 minus 2, maybe something like this. And they both correspond to a negative eigenvalue. So I can immediately draw trajectories on these. On the axis, I have things going straight into V2. I have this, and okay, and in between, you can try to do that. Lambda 2 is the larger in absolute value. So it would look like this. Far away from the fixed point, things look more like V2. Just mix the indices. Things would look more like V2. Yeah. Let's go for the next fixed point. Say at 3, 0, 3, no, 3, 2. Okay, so here trace is -4, determinant is 3, okay, and this is stable, right? 4, 3. This is stable. Eigenvalues. And I'll just give the eigenvectors to save time. Okay, so for this point, it's also a stable regular node, real eigenvalue. We have this second eigenvector V2 on the axis, and -3, 1. Something like this. V1. Now, V2 has the larger absolute value of the eigenvalue. So far away from the fixed point, things will be parallel to V2. Away from the fixed point. Okay, we're closing in on the remaining one. already guess what happened to that. What do you think? What do we have there?
Saddle?
Right. A saddle. Okay, here I'll just give the result. Okay, this is trace equals minus 2, delta equals minus 1. Saddle. Okay, and a negative delta is immediately a saddle. Lambda equals minus 1 plus minus square root of 2. So we have lambda 1 equals 1 plus square root of 2. This is positive. Lambda 2 equals 1 minus square root of 2. This is negative. Actually, I should have started with this one. It's a more instructive example. So I'll just show how I find the first eigenvalue, eigenvector. So I have minus r1 minus 2s1 equal 1 plus square root of 2 times r1. Okay? And then I would add r1 to both sides. And then I have s1 equals 2 plus square root of 2 over 2. Everything with a negative sign times r1. And I can write that v1 equals, for r1 I would just choose 1, simplest, right? And here I would have minus 1 minus square root of 2 over 2. So you can leave it at this, okay? Some people don't like to have an irrational number in the denominator. But you can write 1 over square root of 2 if you want.
So,
Yeah.
shouldn't there be a minus 1 at the delta, on the lower equation on the left?
Lower equation
1 plus square root of 2 on your left?
on the here?
Yeah,
1 plus,
minus 1. Right.
yeah. Okay. Changes everything. Okay. Yeah. Okay. Okay, so we just have r1 equals minus square root of 2 of s1. So we would write 1 minus square root of 2. Okay, so let's do the other one. For the other one, we would have a minus here, okay? And then this would be just plus. So v2, 2 and 1. Okay, then I would like to draw this. At this point, I would approximate. Okay, so I would write that this equals about 1.41. This equals about minus 1.41. But when you are doing your exercise or answering a question in the exam, this is the answer. And especially, do not approximate at this stage. Don't write this as just minus 0.4. Okay, so square root of 2, 1, okay, it's about here, and minus square root of 2, 1 is about here. The fixed point is left empty. 1, 2. Here we don't care, of course, about the values of the eigenvectors, just their sign. Of the values of the eigenvalues, only about their sign. So lambda 1, I mixed them? Yes, I mixed them. So lambda 1 is the negative 1. V1 is minus square root of 2, 1. This is V1. And yeah, it's a positive 1. So V1 is a positive 1. We have growth over that. And we have decay on V2. Okay? So this is what we get. And so now we can start filling this in. Okay, on the axes, it's obvious. Things just go along the axes. Here, for example, you see this might go on into that fixed point, and there should be. Okay, we know that there is some trajectory going into the saddle from this direction. Okay. And the only place it can originate is here. Okay, so we are allowed to connect this. Okay. There is a trajectory here going into the saddle. Let's come from there. Now, also, there is a trajectory going from the saddle into the fixed point. Because everything on this side of the saddle should go into that fixed point. Okay? And this trajectory, I mean, first of all, we have the trajectory going out of the saddle is the eigen direction. Okay? It's on the eigenvector. This is the unstable manifold. So we have here and here things going out of the saddle itself. And it should basically be the same as this one, as the eigenvector here. Okay, we didn't learn bifurcations in 2 dimensions yet, but there is a saddle node bifurcation in 2 dimensions, and it's possible that if we change the parameters of the model, we'll get these fixed points going closer to each other and converging. So at every point along the way, they would have their eigenvectors, even when they're very, very close. And at that point, their eigenvectors would converge to each other.
No, just by the just graphically look at it and it makes sense. Because over here,
well, yeah.
If they don't collapse, it's not possible.
Yeah, probably they do collapse. I don't know. It's not for sure, but I would say that it's pretty safe to connect the eigenvectors of different fixed points with a single trajectory.
Like these two on the x.
Yeah, like these two. But not, for example, 2 of these, because I don't know. Maybe they would converge in a pitchfork bifurcation.
They would connect, but again.
connect their eigenvectors as well. Yeah, okay, this does not have to be a saddle node bifurcation. It could be a pitchfork bifurcation, including all these three. But fixed points should generally meet this bifurcation.
When you say connect them, you don't mean connect them by a straight line.
No.
By a curve.
Yeah, by a curved line.
Could you connect the point at 0, 0 to the point at that's higher off?
Yeah. So here I would have some curvature. Yeah. Okay. This curvature is okay. It's needless. Maybe my drawing is not very accurate, but I don't know what will happen there. But here, things out of 0, 0 go with this curvature, like we found, and here the curvature is different. So we should have some, I don't know, meandering here. And then we have things coming from far away. This should go into these fixed points. This way. We don't know exactly how. There. Oh. Now let's just talk for a moment about what this means. This is a population model, right? So every fixed point here represents a combination of two populations. So we see that on the long term, there are two stable states. One with the rabbits winning, okay? There are no sheep, only rabbits. Here, one with only sheep and no rabbits. And what determines which one we go into, okay? Basically, the initial condition. So we see that, let me mark this with green. There is some curve on the straight plane. It's actually the stable manifold of the saddle that separates, okay? This is the boundary between the initial conditions that lead to the victory of the rabbit and the initial conditions that lead to the victory of the sheep. So this is called a separatrix, this curve. And these two areas are called the basins of attraction. Basin of attraction for their respective fixed points. Okay, and it's exactly like the way water flows down into valleys. Okay, so on the mountain range you would have some line that separates the places where the water flows east or west. Okay, like we have in Jerusalem. What else do I want to say about that? This is not the only situation that we can get from this model. This is just what we get with these parameters that we put here. If we have different parameters, it is possible that we will get the coexistence of the two populations.
Now, what is exactly?
Yes?
What is the definition of basin of attraction?
Okay, basin of attraction is the set. Basin of attraction is the set of initial conditions such that in the long term you go into the fixed point. Now we'll take a 10-minute break and then we come back for the next topic. בדרך כלל גם מבקשים את זה, אבל אם לא רוצים
פה
אז
זה
כדאי.
שם נמצא, אז
הרעיון צריך לשנות סבירות.
אז להציב, כן, בדיוק. ברגע שיצרת נקודה אחת, את יכולה להניח שהחלטות הכיוון שלנו.
גם אם... טוב, כי אין שם.
כן, כן.
יש עוד משהו? ששאלת אותך באמת, אז אמרת לי שאפשר להשתמש בנקודה אחת.
כן.
נגיד אני מוצאת נקודה שהיא יותר אקסטי כזאת. אבל אני
זה יותר כיוון.
כן,
כן.
כזאת. אז אני יכולה להניח את הסימטריה?
כן, כי את יודעת שהכל הולך לתוך נקודת הסרט.
אז אני צריכה לקחת את הזווית הזאת כל הזמן. כאילו, כל הנקודות שמעליי זה...
אוקיי. אני לא יודע.
איך מציירים את זה?
פשוט
אם אתה אומר שאפשר
תראי שזה
בנקודה
הולך
אחת?
מפה וזה הולך לתוך מאוד כאילו אבסטרקט או משהו כזה. אם את רוצה להיות מדויקת...
אם היא קרובה, אבל... אין עליה, אני צריכה לדעת מה קורה אחריה.
אז זה הכל כאילו איזו הרחבה של התבנית.
כן.
אני לא יודע אם משהו בדיוק מעל לי, משהו פה נגיד.
לא, ניסיתי כל מיני דברים. כאילו אני קיבלתי ספירלה שהיא פיתה.
אוקיי, בסדר גמור. את יכולה גם לצייר לה את המיופינות אם את רוצה להיות ממש מדויקת. לצייר לה את המיופינות ולראות איפה יש את המעברים.
כאילו, הם מאוד קרובים. זה אומר שזה פיתה.
כן, נכון. אבל פה הציור צריך להיות הכי כללי, כאילו כל מה שאני מחפש זה הכיוון של הספירלה. זה הדבר היחיד שאת צריכה לעקוב אחריו.
יש לי שאלה קטנה פה, בדבר הזה. ה-notice it can be determined זה לא הוכחה, נכון?
לא.
פשוט רואים כאילו הסימן שזה חיובי או שלילי, הכיוון היה ככה, משל.
כן.
זהו.
אם היית רוצה להתאמץ בזה, היית יכולה לצייר.
כאילו אם הייתי מוצאת את זה הפוך, ולא מה קורה, כאילו...
אוקיי, הייתי יכולה למצוא.
אני עשיתי את בעזרת הספירה.
כן, לא, ברור, אני בזה רציתי לוודא שלא צריך פה איזה משהו מטורף, אלא רק להראות אצלנו בדוגמה, זה מה שקרה.
זה קשור לאוטיז לפי או לאפיין של האוטיזם? כי אני מוצאת קשר ל-B, יש לי קשר לוגי בין B ל-C, אז זה גם קשור ל-C. אז אני חושבת שזה לא מאוד.
לא יודע.
וכאן, מה בדיוק אתה רוצה שנעשה שלא מוצאים את הסיבוב פוינט? כאילו אני מצאתי שיש לי נקודה מסוימת שאם החל ממנה זה משהו מסוים, תחתיה זה משהו אחר. אני יודעת ששני הסיבוב פוינט הם בצדדים שונים, כאילו ביעקוביאן, ולפי זה חקרתי. ולא הבנתי למה אני הבנתי על
לא, חכי. עדיין לא.
שנייה.
לא, אוקיי, זאת דרישה.
זהו, אני כאילו...
זה לא כאילו...
כי ההבנה של כאילו מה קורה פה זה לפי
הרעיון הוא שהאינטגרציה הנומרית תיתן לך איכשהו לבדוק את מה שראית הנומרית. תראי שהדרך שעשית באנליזה המתמטית היא... תראי שהיא בעצם בסוף מתאימה לאינטגרציה הנומרית. כלומר, פה באמת לא יכולת למצוא בדיוק סיבוב פוינט, אבל
אמרתי, היא בין זה לזה וזה בין זה לזה.
כן, ואז, בדיוק, ואז את יכולה לחשוב מה בערך עושה פה. והרעיון שהאינטגרציה הנומרית תראה לך...
כאילו לקחת נקודה מפה, נקודה מפה,
יכולה, אפשר להתייחס לזה כבקשה די גורפת אולי להתקבל כאילו קצת זמן, במיוחד גם שהתרגיל אחרי ההגשה שלו היא בזמן שאנחנו באנגדי. אז זה מין יוצא כזה, אם תהיה אפשרות קצת לרווח את זה שנוכל תהיה
החלק היוצא הוא בסדר, אתה רואה? זה כאילו משהו כן, אז הוא כאילו מפריד במרחב כאילו חלק מהמרחב לשתיים ונקודה שנמצאת פה ונקודה שנמצאת פה אז היא תלך לאיזה נמצאת של השני זה גם באיזה נמצאת של לאיזה מהן זה ילך אז זה הולך לי, זה בדיוק משהו אומר. כן, כן,
זה המודל
אולי שכן, ככה עוד זה.
לא יכול להיות דבר מיוחד במודל הזה.
נראה לי מודל אוכלוסיות. לא, אבל גם הוא אמר עוד משהו, אני יודע אם היית על התופס?
לא, אני לא יכול לדעת אותך.
אז הוא אמר שבתנאים מסוימים, כאילו זה רק בהם יש לו conditions המסוימים שקיבלנו. הוא אמר שהסיבה שבגללה כאילו אינטואיטיבית לחבר את ה-fix point הזאת לזאת זה כי ככל שנשחק עם ה-initial conditions אז הם בסופו של דבר יתאחדו ויהפכו ליצירה.
מה, בפורקיישן?
כן, בדיוק. בפורקיישן מה אתה אומר? שלא למדנו עדיין משהו.
ולזה קוראים הלוסקה רול בטבע, כי זה מה שמגדיר אותו, יש לו את ה...
Right, but I'm saying usually bifurcation is when you have... No, when you study the parameter marks the...
אז לא משתנה.
I mean, you have a parameter and you analyze like a range of values that parameter can receive. Here we can just, you know, you can change every one of the initial conditions to be a parameter and then...
שהוא פשוט מכפלה של ישראל.
זה לא ניתן בכל לוסקה?
לא חייב. אם יש נקודת שבט שהיא יציבה גלובלית. אני לא יודע אם יש פרמטרים שנותנים נגיד כזאת וכזאת ועוד אחת יציבה פה ואז יש שתי ספרטריקס.
The point of it is correct, right?
אם זה היה יציב, אז היה לך את האגן משיכה שלה ואת האגן משיכה שלה ואת שלה. אני לא יודע איך זה נראה, אולי
זה תלוי בעבוד
זה תלוי בפרמטרים של המודל. האמת שאם הייתה פה עוד נקודת שבט יציבה המפעילים
אם יש לך נקודת שבט זה לא כמו 4?
לא, אז באמת אני לא יודע אם יכול להיות מצב שבו שלושתן יציבות. כן, לא בטוח שזה. זאת אומרת, השינוי של אנחנו יודעים מהמערכות החד-ממדיות שבדרך כלל נקודת שבט לא מופיעה יש מאין, כן? או שאחת מחליפה את היציבות ובדרך כלל במפגש עם עוד אחת, או שהיא פתאום תתפצל לשתיים או לשלוש. אז הגיוני שלא יהיה מצב של רק פשוט זאת יציבה איפשהו. כולן כמובן זה פוזיציה אחרת קצת, אבל פשוט זאת יציבה. הגיוני שזה ייראה אחרת.
תנאי התחלה אתה מתכוון לפרמטרים האלה של תנאי...
לא, תנאי התחלה זה נקודות פה, אבל אני מתכוון לפרמטרים אחרים, כן. היה אפשר לעשות, האמת היה אפשר לעשות אולי אנליזה כללית למודל הזה. A, B והרבה קבועים כאלה.
גם שתימצא בדיוק על הספר
זה סאדל, כן.
אז כן יש מצב אחד שבו יש...
נכון, זהו, האמת שסט של הרבה מצבים, נכון. פשוט צריך להתחיל מאוד מאוד מדויק.
כן, אבל כאילו מבחינת האנלוגיה
כן, כן.
יש נקודה
כן,
יחס.
כן, מזל כזה. גם, זה כאילו לא... לא, בעצם אם אתה מתחיל פה ב-0-0 אז גם לא, זה נשאר. Okay, let's continue. Okay, I should have erased the board. Okay, we're moving on to a new topic called limit cycles. I think it's been a long time since I posted the recommended reading material on the web. So if you follow the course on the book and I did not post, please remind me. Okay? Our next topic introduces a phenomenon that can only happen in two-dimensional systems or three-dimensional and up. Something that we did not have in the one-dimensional systems, and we did not have in the linear two-dimensional. Only in the nonlinear two-dimensional systems. This is called limit cycles. And we start with an example. So in this example, we have a fixed point. This is by a guess, basically. We have a fixed point at the origin of axes. And normally we would have to verify that there are no other fixed points, or try to look for other fixed points. We will not do it right now. Okay, let's check what are the properties of this fixed point. Okay, so J at the fixed point. I'll write it first in the general form. So this is 1 minus x squared plus y squared, just by taking the derivative of this product, okay? Minus x times 2x, so this is 2x to the third. Here I have minus 1 minus 2xy. Here 1 minus 2xy. And here 1 minus x squared plus y squared. That's 2y to the third. And then evaluate this at 0, 0. I get 1 minus 1, 1, 1. Have the trace equals 2. Determinant equals 2. Trace square over 4. 4 over 4, this is 1, and this is less than the determinant. So this means that on my determinant versus trace plane, my point is above the parabola. So what I have here sorry. Yeah. Eigenvalues are 1 plus minus I. Where? Here? No. Yeah. Sorry. I see what you mean. And this is also. Yes. Okay. Okay, yeah, and then we could simplify this. But it doesn't matter. It's just substituting 0, 0. Let's turn on the projector. Okay, so this is a spiral. I hope we get the projector soon. I forgot that I have an example for this. Okay. Okay, I did not draw an oak line. I'm choosing initial conditions, and you can see this. We have a spiral going out of the origin, and it seems to be converging to a single circle. Okay, everything is going into the circle. And what happens on the circle is that the system keeps revolving. Yeah. Okay, so this is a special form of oscillations that is called a limit cycle. Okay, and the definition of a limit cycle is an isolated closed trajectory. So this means that there are no neighboring closed orbits like we had with the center. Remember? The very first example of the Romeo and Juliet model, I think, had this center at the origin, and if you would go away from the origin, you would revolve. And if you would move a little from the circle, you would revolve in a circle that is just a bit wider. So those are not isolated closed orbits. These around the center, they're not isolated. This limit cycle is isolated. If you perturb from it, you go back to it. You don't have a neighboring closed orbit. Okay, so a limit cycle can be stable, like this one, or you could call it an attracting limit cycle. It could be unstable. So an unstable limit cycle would be a circle where if you are on it, then you would keep revolving in the circle. But if you are just off it, you would spiral away. Or if you are inside, you would spiral into a fixed point. There is always a fixed point inside the limit cycle. Okay? At least one. Could be three, maybe. Always at least one fixed point. And there could also be a half-stable limit cycle, which means that if you, for example, if this were half-stable, if you start from out of this limit cycle, you would spiral and go on to revolve around the limit cycle. And if you start a little bit inwards, you would run away from it and spiral into the center. That would be a half-stable limit cycle. Let's mark it like this. So actually, I don't know how to mark it. I don't know for a convention about. Yeah. Let's say that we mark a half-stable limit cycle with a solid line, because we do have a trajectory there. Okay. If I would have different colors, then I would use like a dashed black line to mark the limit cycle, but a blue line for the trajectory. What? Say again? So unstable, I would. Okay. This is universally marked with a dashed line, so it would look like this. On the cycle, yeah, a single one. Yeah.
The trajectory is coming out.
Okay, let's do this dashed as well. I never really gave thought to it. Yes.
The trajectory is coming out of the cycle. So do those have to be pointing outward, unstable? Like, what are those?
These on the unstable?
On either the outward one. So are things outside of the cycle coming into the cycle, or can it be the other way around also? Because the idea of a cycle is that it's supposed to circle. Like, once you're in the cycle, you're not supposed to leave, right?
Yeah.
So the trajectories pointing towards the cycle always have to be inward?
Outside, if it's a stable cycle, then if you're outside, then you go into the cycle. Yeah, inwards.
Okay, and if it's an unstable cycle?
Then they would go outwards.
So then
like here.
So what's cyclical about it then?
If you are on it, then you would be trapped on the cycle.
Okay, but if you're... So what would be a situation where you leave?
If you are just a bit off the cycle.
Okay.
Okay. Okay, so these are limit cycles, and the reason that they are so interesting is that they allow us to describe oscillations that are often encountered in physical systems. So they might describe oscillations in the firing rates of a neural network, or repeated firing of some neuron, or they could describe vibrations in some mechanical system, for example, a bridge. Okay, then your parameters would represent movement and maybe velocity as well to different directions. Yes?
How do I know the direction of limit?
The direction of how the limit cycle turns?
Which is clockwise or counterclockwise?
You don't. If you remember in your exercise, you could find that you could find the direction around this spiral according to the structure of the matrix of linearization. So if you do that, then you have the direction of the limit cycle. Okay? But there is no rule for, except for maybe the direction of the spiral and the fixed point that's inside the limit cycle. But other than that, you can substitute. You do a simulation.
So I don't know if I know the direction inside the cycle, inside the circle.
Yeah.
But it doesn't mean that it's the same direction outside.
It does, because maybe except for the half stable where I'm not sure what would happen. No, I think it should still be the same direction. If it's a stable limit cycle, then you can come from here and you can come from here, and the limit cycle has a direction, so everything should agree with that. Okay. Also, if it's unstable and so on. Yeah.
What is the direction of the inside of the half stable?
Of the
Going
inside.
to the center?
Yeah.
Yeah.
Mhm.
Because the stable one wasn't going to the center, right? It was going to the circle.
Yeah. Okay. Yes.
Another question. Does it, we found fixed point here at 0, 0. And
Yeah.
we know that it has to be an unstable fixed point for the cycle to be a stable cycle.
Yes.
Right? So it means that I can tell the direction of the circle from
From
the
the
eigenvectors of the, or from the imaginary part of the
yes.
fixed point.
Yes. Okay. Yeah. So that will be similar to having a rule on this matrix. Okay. Okay. Another important thing about limit cycle is that it has a fixed period and a fixed amplitude, of course, and also a fixed waveform. So if this were not a circle, okay, that would be an ellipse. Sorry, the limit cycle doesn't need to be a circle or an ellipse. It can be some very curved structure in space, in the phase space. And we'll see that actually with the next example, so I won't go into that. Now, so amplitude, obviously, if you look at the amplitude on X, you see that it's fixed, and also on Y. It doesn't matter the shape of this.
So the radius is just mean by amplitude?
Yeah.
Okay.
Depending whether you define peak to trough or just the radius. And period, it means that the limit cycle will always have the same frequency of this oscillation. Okay? This system settles to an oscillation of a certain frequency determined by the parameters. Okay? Okay, now there is no way to tell, there is no, yes.
Can you, regarding this question, if we think of it as oscillation, can we consider it oscillation with decay? Meaning that when it reaches the center, it kind of decays to 0?
Wait a minute. This one, this one is, no, actually, oh, this one maybe.
Right.
Yeah, okay, this is just a spiral, okay? But we're interested in more, actually, in the stable limit cycles, where every initial condition would lead to a, yeah, okay? Now, the important thing is that there is no general way of telling whether a system has a limit cycle, okay? There is no analytical criterion that will tell you in advance that a given system will have a limit cycle. There are several ways of ruling out limit cycles. So we have several tools of saying of being given a system and saying this system does not have a limit cycle. So if you wanted to say whether a system has a limit cycle, you would take the system, you would try tool A, tool B, tool C. You would see if you manage to rule out a limit cycle by any of these tools. And still, if you ruled out with all, sorry, if none of your methods ruled out the limit cycle, you still don't know if it doesn't mean that there is a limit cycle. Okay, so it's kind of we can test the system in several ways, but nothing ensures us that we will find that there is a limit cycle. And there is one way of showing that there is a limit cycle in a system, but it doesn't apply to all systems. Okay. And we'll see several of these. So the first method is switching to polar coordinates. Okay. Let's see.
It's a method for showing that it doesn't have a
A method for showing that there is a limit cycle, or isn't. Let's do this. No. Okay, switching to polar coordinates. I don't know if all of you know, but the Cartesian coordinate system is not the only one that we have. We also have polar coordinates on the two-dimensional space. And here we have R, which is, sorry, it's better to show this. To describe points with the polar coordinates, we use two coordinates. We use R, that's the distance from the origin, and we use theta. That's the angle from the x-axis in the counterclockwise direction. Okay? So, by Pythagoras, we have r equals x squared plus y squared. And I take a square root of that. And from trigonometry, we have theta is the arctangent of y over x. So this is the shift between the two coordinate systems. Okay. Now, we would like to switch from our system, this one, to the polar coordinates. Okay. And basically, we are asking what is r dot and what is theta dot. How do these two variables change with time? Okay. So what we do is basically we take the derivative with respect to time. This is a bit complicated. Okay, so I'll do something else. Okay, I'll say that r squared equals x squared plus y squared, and then take dt of that, and then I get 2r dot equals 2x dot is 2y dot, and then I can write r dot is just x dot plus y dot divided by r. And I can replace this with that, of course. Okay, if I want everything to be an x and y, but it doesn't matter for me. Okay, theta dot. This is easier. Okay, 1 over 1 plus this squared. And then I need the inner derivative. And I have minus y x dot. this. And I could write r squared here. Doesn't matter.
What you did with theta is just substitute.
I took the derivative of this,
Uh-huh.
of the arctangents. This is 1 over 1 plus the argument square. And then I took the inner derivative of, f prime g minus ft prime over g squared. Right. So basically, I have these two relations. I'll write the theta dot again. I have this. And then if I want to know r dot and theta dot, I just substitute my given system into x dot and y dot. Okay, if I do this for that system, it's a little long. So I have x squared minus x squared times. Right, I just took x times x dot plus y times y dot. This goes away. Yeah?
You're only substituting the x dot and the y dot
Yeah.
according to.
Mm-hmm. Okay, so what I have here is x squared plus y squared minus x squared plus y squared times x squared plus y squared. And remember, this x squared plus y squared is just r squared. And if I do this for theta, okay, for some reason I used to write this differently, so I'll just retain that writing. Okay, equals plus 1. So our system written in the new coordinate system looks like this. Now, these equations are uncoupled. Okay, there is no theta in the r equation, and no r in the theta equation. And this is a system we already know, right? Let's try here. Remember, r cannot be negative. Okay. Yeah.
When you wrote the r dot function,
Just a moment. Yeah.
shouldn't it be
No, because this canceled with one of the powers, and then I took out one r. So we know this system, right? The logistic system. So we have a stable fixed point on r. This means that there will be a certain radius which is stable. Okay? And that's our limit cycle. What the theta dot tells us is that the oscillation is always counterclockwise. Okay, it's positive, and it's always at the same rate, the same radial velocity. Okay, so switching to polar coordinates was perfect for this system, and it's good for a system where you have expressions like this. Okay. Or even if you have expressions like this, that's also nice, because then you would scale x and y according to a certain scaling, and eventually reach some r, some elliptical coordinates.
So how did you prove that we have or don't have?
Say again?
We have a limit cycle or not?
We have, because there is a fixed point on r. Okay? If there is a fixed point on r, you no longer care what happens with theta, because you know that once you reach that r dot is 0. You don't go out of that.
So we can only prove that we don't have a limit cycle, no?
No, I meant that, yeah, in specific cases you can prove you have a limit cycle. I also said there's one tool to prove that you have a limit cycle. It's not this one, it's another one. But you don't have something that's general for all systems. I mean, moving to polar coordinates will not always work, and a lot of limit cycles are just not so symmetric. Okay. So maybe if you would manage to write them in polar coordinates, it will be a very complex transformation. But this is good for some systems. Okay, the next thing, yes?
What is the meaning of the theta of the equality 1 theta? That the theta equals 1?
Theta dot equals 1. That it's
Not changing.
it's changing. Theta is changing. Okay. Okay. We'll finish this lesson with an example for a system with a limit cycle. And then in the next lesson, which is currently our last for this semester, we will cover the methods for ruling out limit cycles and the theorem for showing that there is a limit cycle. Okay, our system is called the van der Pol oscillator. And it was studied a lot, and it actually gave a boost to the field of dynamics because it is relevant for electrical circuits in radios. So when people started building radios, we started investigating this system. Okay. We did not see a second time derivative yet, right? And I'll show you one of the reasons that I showed the system is to show you how we deal with the second time derivative. Um, and if you know a little of about electricity, then you would realize that this is describing some RCL circuit. Okay, so we have a term for the charge, and a term for the current, and a term for the induction. And basically, this term is a restoring force. Okay, it's like the hook law of the spring, right? So this is some restoring force, and this is a damping. In equations of motion, the x dot would be the velocity, and the b term would be the coefficient of friction, which dampens the movement. This is similar to what you would have if you would write an equation for an object falling through air. So you would have something like this. Coefficient of friction. Okay, let's say, which is like writing MA equals mg h minus 0. Yeah, something like this. The projector, but I want it for later. Sorry. I can turn on the light. Okay. Okay, so this is our system. These were just analogies to show you that this is a restoring force, and this is a damping. It's kind of friction on the system. What? Yeah, it depends how you write it. So if it were here, it would be a minus b, right? So that would actually dampen your system. So a positive b here dampens your system. Okay. Okay, so in the van der Pol oscillator, we have C equals 1, M equals 1, and B is some nonlinear function of x. Our function is mu times x squared minus 1. Okay, and like I said, positive b is a damping. Okay, and negative b would be a kind of driving of a divergence. So you see that if we have x larger than 1 in absolute value, we would have damping. And if we have x smaller than 1 in absolute value, we would have, what did I call it? I didn't call it. Let's call it driving.
So it's not the b, it's the x?
So, excuse me? So b is a function. And we see from here that if b is positive, we have damping. And then we can ask, when is this function positive? And this is, of course, when mu is positive. Yeah. Okay, now this system has one variable, x. Okay, and we never dealt with systems of one variable but two time derivatives. But what we do here is we use this trick. We define a new variable y that is just x dot. Okay, so if I write the system again, already substituting my expressions, okay, then what I have here is y dot plus mu times x squared plus 1 times y plus x equals 0. And this is how I got my y dot equation. Minus x minus mu is x squared plus 1 times y. And my x dot equation just comes from here. And this is what I have. So now I have a two-dimensional system with only first-order derivatives. And I know how to deal with that, okay, with our geometrical methods and so on. Okay, so this system has a fixed point at 0, 0. You can easily see that any fixed point would have y equals 0. And then if you substitute it here, you must have x equals 0. So fixed point at 0, 0. J at this fixed point. I'll give you just the final answer. It looks like this. So the trace is mu, and the determinant is 1. So we have a stable or unstable fixed point depending on the value of mu. And the value of mu would also determine whether this is a spiral or not. Okay? As you can see here, lambda is mu over 2 plus minus mu square minus y minus 1. This is 4. It should be 4 over 2. So if mu is larger than 2 in absolute value, is smaller than 2 in absolute value, you'd have an oscillation. You can also find the null lines. X dot equals 0 gives you y equals 0. That's just the x-axis. And the second null line, y equals x over mu times 1 minus x squared. Okay, so I'm going to finish with just showing a simulation of this in MATLAB. And it serves, apart from as an example for how we deal with the second-order derivative, it serves as an example for a limit cycle that is really not symmetric. Okay, what I have here is the two null lines. Remember, y equals 0. And that null line, x over mu times 1 minus x squared. This is the green line. Okay? And the fixed point at the origin. And yeah, I took mu equals, let's see, 0.3. Okay. And here I plot the x and y, the x and y versus time. Okay, so I'm converging to this kind of steady oscillation. Let's take a different point here. And the reason I'm showing you x and y, which is actually x dot, is because in the original system we only cared about x. Okay, that would be the charge, for example. We only cared about x. So this is how x oscillates on its own one dimension. And this is the velocity of x. And what this system shows you is how you can get a very non-symmetric limit cycle, okay, which would give you a waveform that is, it's not a sinus or a cosine. It's not a sine or a cosine. It's some more complex waveform. But once you're in the limit cycle, you repeat this complex waveform. Okay, it's consistent, and you have a consistent amplitude for this waveform, a consistent period, and so on. Okay, this is the end of this lesson. Next week we'll see the different methods for dealing with limit cycles. And it's too bad that in this semester we did not have a chance to finish the dynamics part and talk about chaos. Okay, so it's in part because we lost one lecture for the ISFN. So we'll either make it up in the beginning of next semester, or we'll do an additional lesson or an additional hour to one of the lessons.
מה קורה כש-x נגיד שווה ל-1? לא, b שווה ל-0. ובמקרה הזה נגיד x לא יכול להיות שווה ל-1, כי אז
x שווה ל-1.
פה אתה לא יכול להשאיר, אבל כאילו מלפני זה, כשעברת ל-b. כן, פה זה צריך להיות מינוס 1. רגע.
כן, אז x שווה ל-1,
אין את b, זאת אומרת יש רק את החלק של n ואת החלק של c.
סטוקסטית,
היא בוחרת את התוכנית
אבל הווייבפורם
זה לא רגולרי,
לא
סינוס רגולרי,
ממש...
יש משתנות,
כאילו, אתה יודע, במקום סינוס שנראה ככה, אז אולי זה כאילו משהו אחר. אז אתה יכול, נגיד, במודל שאני סיפרתי בדוקטורט, אז האוסילטור ההרמוני, מה שהוא נותן לך זה קצב ירי של רשת שנראה, נגיד, ככה, כן? אז יש לך פתאום ספייק, ואז...
ספייקים קבועים בזמן?
כן, אז זה קבוע בזמן, ה-waveform הוא אותו waveform תמיד, זה אמפליטודה, זה פשוט, זה מאוד לא רגולרי, כן? זה הרעיון, שהרבה פעמים במיסטייקל יכול להיראות נורא שונה. נגיד, לפי פליין שאני חקרתי,
אבל לא בסוף, הוא הגדיר את מי לא נגד שישחק שווה וואלה והגדיר את זה
אני נקודה שבט פה ושנקודה שבט פה, אני שונה.
ואני חושב שתי נקודות
זה היה. אני לא זוכר, אבל המיסטייקל נראה משהו כזה.
אפילו לא עגול?
כן, ממש לא עגול, וגם את הקטע הזה עושה ממש מהר, זה הספייק, הקטע הזה עושה נורא לאט. אז זה כאילו קטע.
מתי עשית את זה? זה עכשיו? זה לא משהו...
אני עכשיו, אנחנו מנסים לסיים את המאמר, אבל עשיתי את זה בשנה, שנתיים ראשונות של הדוקטורט. במקביל להתחלה של העבודה המקצועית.
וכאילו עשית את זה לפי תוצאות של עבודה מקצועית?
לא, עשיתי את זה כי אנחנו רצינו לעשות קלסיום אימג'ינג וניסינו לקבל פרדיקציות לקלסיום. אז מערך מודל שאלי פרסם, אלי היה כתוב עליו, אבל זה מישהו ממכון ויצמן בשיתוף עם זה, והוא ייעץ להם. אז אני לקחתי את המודל בשביל לספק פרדיקציות העבודה המקצועית, ועברתי על המודל וניתחתי את זה.
אז כאילו היה לך דאטה של עבודה מקצועית ואתה ניתחת אותו והייתם מנוע?
לא, זה לא גם נכון.
זאת אומרת שהדאטה, המודל הזה שהם בנו היה גם?
לא, המודל בדק כל מיני, ניסה בעצם להפיק תופעות כמו שרואים בקורטקס אודיטורי ובפיזיולוגיה, כן? אבל הם לא בדקו נגיד פרדיגמה של התופעות. אז אני פשוט לקחתי את אותו מודל שכאילו אמר, טוב, אם מודל כזה הוא הגיוני להסביר את הקורטקס אודיטורי כי הוא נותן את הטיונים של הגאלה וכו'. ואז אנחנו אמרנו, טוב, אז ניקח את המודל הזה ואיך הוא מגיב ל-SSA, אם יש בו SSA, אם הוא מספיק את זה להסביר SSA, ואז הרצתי את המודל הזה, אז כאילו מצאנו שיש SSA, ואז התחלנו לחקור את ה-SSA במודל קצת, ולא הגענו עדיין לעשות את הקלסיום אימג'ינג, שיכול אולי לאשש את המודל או לשפר את המודל. אנחנו, השיטה שקמיני ודינה משתמשות בה עכשיו היא קצת, היא אחת השיטות, היא שיטה שעשתה במעבדה ואף אחד פשוט לא הצליח לשחזר אותך. ועדי אמר לי וגם לעוד אחרים, אז הזריקה של הפלורסנט דאי, הפלואופור,